Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the heart of the darkness itself, into the places where light rests and time slows, the black holes. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the cores of black holes together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Before we reach the event horizon or touch upon the mysteries of singularities, it's worth slowing down and starting where it all begins, with gravity. You and I are both feeling it right now, though perhaps so constantly that it has become invisible to us. It presses you gently into the chair or the bed. It draws the cup of tea down toward the table. It sways the branches outside in the wind. Gravity is the most patient of forces, doesn't hurry, doesn't shout. It works in silence, whether holding the moon in its long embrace or persuading a leaf to fall to the ground. Our story tonight could have started anywhere in the universe, but gravity is the stage on which all of it unfolds. It is the quiet sculptor, shaping the gas and dust between the stars into worlds, shaping the stars themselves, and ultimately shaping the black holes that are born when even the mightiest stars run out of fuel. The physicist Isaac Newton imagined it as an invisible thread, pulling every object toward every other object, its strength depending on how heavy those objects were and how far apart they stood. 2 centuries later, Albert Einstein would come along and tilt that picture sideways. To him, gravity was not a thread, but a bend, a graceful curve in the fabric of space and time. The more massive an object, the deeper the bend, and anything passing nearby, whether it be a planet, a star, or a beam of light, would follow the curve without question. One way to picture it is to imagine a stretched rubber sheet. Place a marble on it, and it rolls along in a straight path. But set something heavier down, a bowling ball perhaps, and the sheet dips, creating a gentle well. Roll a marble now, and it will spiral inward, not because it is being tugged by some invisible hand, but because it is simply following the slope in the sheet. In the same way, Earth follows the curve the sun creates, and the moon traces the curve the Earth makes. The sheet is, of course, only an analogy. Space is not a fabric you could touch, and the universe is not stretched over a table. But the image is useful because it gives us a glimpse of how mass shapes motion and how the presence of something enormous can subtly direct the path of everything around it. Gravity's reach is absolute in its patience. It takes millennia to gather a star from a drifting cloud, coaxing every atom toward the center. It pulls on the oceans, breathing the tides in and out. It presses the atmosphere close to the planet, allowing you to take that next slow, unthinking breath. And yet it can be fierce. A collapsing star proves that. When enough mass is concentrated into a small enough space, the slope in that cosmic sheet grows so steep that nothing, not even light, can climb out again. That is the threshold we call an event horizon, and somewhere inside, unseen, is the core that tonight's journey is about. But before we rush ahead, we can linger here, in the comfort of this slow beginning. There is something soothing in thinking about gravity not as a threat or a trap, but as the reason there is anything at all. Without it, the universe would have been an endless fog of particles, each moving on its own, never meeting, never forming the suns and planets and living things we know. The night sky would be dark not because of distance, but because there would be no stars to light it in the first place. Everywhere you look, gravity is holding stories together. A spiral galaxy with hundreds of billions of stars stays intact because every star is listening to the combined pull of all the others. Even the most delicate structures, the rings of Saturn, the dance of two moons passing close without colliding, are part of its choreography. And here on Earth, you and I are participants too. Your bones are shaped to stand upright under its pull. Your muscles have learned to work with it since before you could walk. Your sense of balance depends on it. In a way, gravity is part of the language your body speaks without ever thinking. It's easy to think of the vastness of space as remote from our daily lives, but in truth, we are bound to it. The same laws that guide the arc of a comet also guide the arc of a thrown pebble. The same mathematics that explains the fall of an apple can be used to chart the slow circling of two stars around each other. We live in one story, not two. The domestic and the cosmic are written in the same hand. As we drift into this exploration, you might think of yourself as floating just above the Earth, looking down at its curves and oceans, feeling its pull. That pull will be our thread, leading us outward towards stars heavy enough to collapse in on themselves, and inward toward the places where gravity becomes something stranger than even Einstein could fully describe. Tonight, we will follow that thread patiently, letting it take us past the familiar and into the quiet depths where black holes hide their centers, and through it all, the weight you feel now, that soft, unshakable pressure holding you, will be our constant reminder. We are not separate from the universe we are about to explore. We are resting inside its embrace. If gravity is the gentle hand that holds everything together, then stars are its most luminous works of art. We often think of gravity as something that pulls things down, but it is just as much a builder as it is a holder. Every star you have ever seen, from the faint pinprick in a clear winter sky to the overwhelming blaze of the sun, is a creation of gravity, coaxing loose, cold gas into something hot enough to shine. Without that pull, the universe would have remained a silent mist of particles, each adrift in its own direction. It begins in darkness. In some quiet corner of a galaxy, far from the restless glare of the core, a cloud of gas and dust floats, seemingly still. But stillness is an illusion. Every atom in that cloud is feeling the subtle nudge of every other atom, a countless web of tiny pulls. Over time, and time here is measured in millions of years, the cloud begins to gather in on itself. Small knots form, pulling in more material, their gravity growing with every addition. What was once diffuse begins to thicken. As the matter falls inward, it speeds up, and with speed comes heat. Deep at the centre of the cloud, temperatures rise until something remarkable happens. Hydrogen atoms, which have floated unchanged since the birth of the universe, are pressed so close together that they fuse. In that instant, the star is born. Fusion is not just the star's light switch, it is its heartbeat. For as long as it lasts, fusion produces enough outward pressure to push back against the inward pull of gravity. This balance is delicate but steady. On one side, gravity insists on pulling the star into a tighter and tighter sphere. On the other, fusion pushes outward, a continuous expansion trying to resist collapse. For millions or billions of years, depending on the star's mass, this quiet argument stays in perfect equilibrium. The sun is living through its long middle age in such a balance right now, and will continue to do so for billions more years. But not all stars are so leisurely. The truly massive ones, 10, 20, even 100 times the mass of the sun, live fast. They burn through their fuel at an astonishing pace, their cores roaring with fusion. They shine brighter, hotter, and shorter than their smaller siblings, their lives measured not in billions of years, but in mere millions. Inside such a star, fusion follows a ladder of elements. It begins with hydrogen fusing into helium. When the hydrogen runs low, gravity wins a small victory, squeezing the core tighter until helium can fuse into carbon and oxygen. The process repeats, gravity pushes, the core heats, fusion of heavier elements begins. With each step, the fuel becomes more difficult to burn, the temperature's higher, the star's life shorter. Eventually the ladder reaches its last rung, iron. Unlike lighter elements, iron does not release energy when fused. Instead, it consumes it. The star, for the first time, cannot respond to gravity's push with an equal burst of outward force. In that moment, the balance breaks. Gravity, patient for millions of years, finally has no opposition. The core collapses in on itself in a fraction of a second. The outer layers, no longer supported, rush inward too, then rebound off the collapsing core in a titanic explosion. A supernova. For a brief moment, the star outshines its entire galaxy. In those few days or weeks of brilliance, the blast forges elements heavier than iron, gold, uranium, iodine, scattering them across the cosmos. These are the atoms that will one day find their way into the crust of a planet, the cells of a tree, the bones of a human hand. What remains at the very centre after the explosion depends on the mass of the core. If it is small enough, it becomes a white dwarf, a hot, dense ember that will slowly cool for trillions of years. If it is heavier, the atoms are crushed so completely that protons and electrons merge into neutrons, forming a neutron star, a sphere only a dozen miles across, yet more massive than the sun, spinning rapidly and shining with beams of radiation. But for the most massive cores, even the pressure of neutrons cannot halt the collapse. Gravity overwhelms every known force, crushing matter beyond recognition. The collapse does not stop until the mass is compressed into a region so small and dense that the space-time around it curves inward completely. Light, once free to travel, now cannot escape. An event horizon forms, the point beyond which no signal, no message can return. A black hole is born. These stellar mass black holes, as we call them, are the most common type we know. They range from a few times the sun's mass to perhaps a few dozen, each one a silent relic of a star that burned brightly and died young. We cannot see them directly, for they emit no light, but we can see their influence. In some cases, a black hole shares a system with a living star. Its gravity pulls matter from its companion, forming an accretion disk, a swirling ring of gas spiralling inward, heating to millions of degrees, glowing in X-rays before vanishing across the horizon. In other cases, a black hole drifts alone, invisible until it passes in front of a distant star, bending the star's light with its gravity in a fleeting event called gravitational microlensing. It is strange to think that something so powerful can be so quiet. Most black holes are not ravenous monsters devouring everything in sight. They simply exist, curving the space around them, waiting for anything that wanders too close. And yet, given enough time, they can change the fate of entire systems, drawing in gas, pulling on stars, subtly altering the paths of planets. All of this, the birth of stars, their long balancing act, their collapse into black holes, is gravity's doing. The same force that keeps your feet on the floor also pulls clouds into suns and suns into darkness. It works on scales so vast that human lifetimes seem like moments in its plan. And in the quiet between the explosions and the collapses, gravity keeps on working, always patient, always present, guiding the universe toward its next chapter. As we move forward, we'll follow that chapter deeper into the darkness, toward the event horizon itself, the thin, invisible veil where the story of a black hole's surface ends and the mystery of its interior begins. But even there, in the deepest shadow, we'll carry this understanding. Nothing we encounter is separate from the quiet pull that began with a falling apple and ends with falling stars. When we look up at the night sky, it is tempting to imagine that every star is much like our sun, a steady, constant beacon that will burn for billions of years. But not all stars live such slow, measured lives. Some are born already destined to burn faster and die sooner, carrying within them the seeds of something far stranger. These are the massive stars, the giants whose brilliance is both their glory and their undoing. The difference between a small star and a massive one begins at the very moment of birth. A small star forms from a modest cloud of gas and dust, collapsing under its own gravity until the temperature at its heart rises just enough for hydrogen atoms to fuse into helium. Once that fusion starts, the star settles into a long, stable rhythm. It sips its fuel slowly, living a life that may last tens of billions of years. A massive star, however, begins life with a much larger store of fuel, but it burns through it at a ferocious rate. Its core roars with fusion, producing an outpouring of energy that pushes back against gravity's relentless inward pull. This balance between the outward pressure of fusion and the inward grip of gravity is what keeps any star whole. It is like two hands pressing together, neither yielding, their meeting point held steady. For millions of years this balance holds. In the core of a massive star, hydrogen is steadily transformed into helium. This is the first step on what astronomers sometimes call the stellar ladder, a slow ascent toward heavier and heavier elements. When the hydrogen in the core is depleted, gravity gains a momentary advantage, squeezing the star's heart until it grows hot enough to begin fusing helium into carbon and oxygen. The star does not resist. It simply adjusts, finding a new balance at a higher temperature. The cycle repeats. Each time the core's current fuel runs out, gravity presses harder, and the star responds by climbing to the next rung on the ladder. Carbon into neon, neon into magnesium and oxygen, oxygen into silicon, and eventually silicon into iron. Each stage burns more quickly than the one before it. What once took millions of years now takes mere months, weeks, or even days. The star's life accelerates toward its conclusion, as though aware that its time is running out. And then, iron, here, the ladder, ends. Fusion is an act of combining light elements into heavier ones, releasing energy in the process. But with iron, the rules change. Fusing iron does not release energy, it absorbs it. Instead of pushing back against gravity, iron offers nothing. It is a dead weight in the core, a silent passenger in the star's heart. For the star, this is the moment the music stops. Gravity, patient and watchful for millions of years, finally finds no resistance. The core begins to collapse, not slowly but catastrophically in a fraction of a second. Temperatures skyrocket to billions of degrees. The innermost layers are crushed until even atomic nuclei are broken apart. Around this imploding heart, the rest of the star's layers fall inward as well, moving at a significant fraction of the speed of light. They crash into the collapsing core and rebound outward in an immense shock wave. This is the supernova, a detonation so bright it can outshine an entire galaxy for days or weeks. In that furious light, elements heavier than iron are forged. Gold, platinum, uranium. The blast hurls them into space, scattering the raw materials for future planets, oceans and living beings. The core that remains after the explosion is forever changed. If the star was on the lower end of the massive scale, its remnant may be a neutron star, an object so dense that a single teaspoon would weigh more than a mountain, spinning rapidly and sending beams of energy sweeping through space. If the star was more massive still, the collapse will not stop at neutron matter. Gravity will continue to pull, overwhelming even the immense resistance of neutrons packed shoulder to shoulder. The core will shrink past any physical structure we can imagine, beyond the reach of known physics, until it becomes a black hole. In the life of a massive star, this ending is written from the very beginning. It is a life lived in extremes, fierce light, crushing pressure, and a race through the elements that smaller stars will never know. Yet for all their violence, massive stars are also the great benefactors of the universe. Without them, there would be no gold in a wedding ring, no iodine in the salt on your table, no iron in the blood moving quietly through your veins. When you look up at a bright star, it may be easy to forget that you are, in a way, looking at part of your own history. The carbon in your cells, the calcium in your bones, the oxygen in every breath you take, all were formed in the hearts of ancient stars that lived, burned, and died long before the sun was born. The lives of massive stars may be short, but their influence endures for billions of years, woven into every living thing. And so, the story of the black hole begins not in darkness, but in blinding light. It begins in the furious heart of a massive star, in the delicate balance between outward pressure and inward pull, in the steady climb up the stellar ladder, until there is no rung left to climb. Soon, that balance will be lost and the star will surrender to gravity entirely. When it does, the universe will briefly flare in a spectacular display before falling silent, leaving behind only the most enigmatic of all cosmic objects. That surrender, and what comes after, will be the subject of our next step in this journey, as we watch the balance tip, the collapse unfold, and the birth of darkness begin. The life of a massive star is a balancing act so steady that it can seem eternal. For millions of years, fusion and gravity press against one another like two palms in an unyielding handshake. But that final rung of the stellar ladder, iron, changes everything. It is the point where fusion can no longer provide the outward push. And when that happens, gravity's patience ends. The transition from balance to collapse is not gradual. It is not the slow drifting of a leaf toward the ground or the long, gentle fade of twilight into night. It is sudden, a change that unfolds in less than a heartbeat. Inside the star, the iron core, unable to resist, begins to shrink. At first, the outer layers do not notice, but as the core compresses, gravity's pull strengthens, dragging everything inward. The collapse accelerates. Atoms, once neatly arranged, are squeezed so tightly that the spaces between their particles vanish. Protons and electrons, crushed beyond recognition, merge into neutrons, releasing a burst of neutrinos that stream outward at nearly the speed of light. These ghostly particles carry away a vast amount of energy, but they barely interact with matter, passing through entire planets as though they were made of mist. The collapse continues until the matter at the centre reaches densities so extreme that it is, in a sense, solid neutron matter, a kind of cosmic city where every building is a neutron standing shoulder to shoulder, with no room for even a whisper of space. If the core is small enough, this pressure is enough to stop gravity's inward rush. The result is a neutron star, spinning fast, its magnetic field sweeping space like a lighthouse beam. But if the star is too massive, even this neutron wall cannot hold. This is the moment when the known laws of physics, the ones we've tested and relied upon for centuries, begin to falter. The core shrinks past the limits of any matter we understand. The Chandrasekhar limit, which tells us when white dwarfs collapse, and the Tolman-Oppenheimer-Volkoff limit, which describes the maximum mass a neutron star can bear, are crossed. Gravity becomes absolute, folding space inward so steeply that there is no turning back. While this is happening deep in the core, the outer layers of the star are still falling inward. When they strike the now incredibly compact centre, the impact sends a shockwave roaring outward. In the split second that follows, the star explodes. This is the supernova, a bloom of light so bright it can be seen across millions of light years. For a short time, the dying star rivals the brilliance of all the stars in its galaxy combined. The energy released is staggering. Entire solar systems could be swept clean by the force of it. In this moment, the heavy elements forged in the star's final moments are cast into space, mingling with the debris of earlier generations of stars. This is how the galaxy enriches itself, each death seeding the future with the ingredients for planets, oceans, and life. If the collapse has formed a neutron star, the story ends here, with a remnant spinning in the dark, slowly cooling over eons. But if the collapse has gone further, beyond even the neutron stage, then the heart of the star has become something far more mysterious. Space and time themselves curve inward toward it, and an event horizon forms. An invisible boundary that marks the place where escape is no longer possible. On the outside, there is nothing to see except the fading glow of the supernova, and perhaps the slow drift of matter toward the new black hole. But on the inside, where gravity has pulled everything past any resistance, the future narrows to a single direction, inward. Whatever once made up the star, atoms, particles, forces, is now compressed into a region no one can observe and no current theory can fully describe. We call it a singularity, but the name is just a placeholder, a signpost at the edge of our understanding. It is strange to think that something so spectacular as a supernova leads to something so silent. The black hole does not roar or blaze. It does not announce itself except by the way it bends the paths of nearby stars or draws in gas that strays too close. In time, even the memory of the supernova fades, and the black hole is left alone in the dark, invisible except to those who know where to look. And yet this quiet is deceptive, for though the black hole may rest in stillness, it is a place where the laws of nature are stretched to their limits. Every black hole is in a way a question. What happens beyond the event horizon? What becomes of matter and light once they cross that boundary? Does the singularity truly exist as our equations predict? Or does some deeper truth wait to be uncovered? We owe our very existence to events like these. Without the collapse of massive stars, without the supernova shock waves that scatter heavy elements through space, there would be no Earth, no oceans, no air to breathe. Your body, your bones, your blood, all carry the signature of ancient stars that lived fast, died young, and collapsed into darkness long before our sun was born. It is easy to think of black holes as endings, but in truth, they are part of a cycle. Stars are born from the debris of those that came before. They burn, they shine, and eventually they return their material to the cosmos, where it may gather again into new stars, new planets, and perhaps even new forms of life. In the quiet that follows a collapse, the universe is already preparing for what comes next. In our next step, we will cross that invisible boundary, the event horizon, and see what it means to reach the point of no return. But for now, we linger at the moment of transformation, a star's final heartbeat, the instant when gravity wins. From a distance, a black hole is just another part of the cosmos. It tugs on nearby stars, bends the paths of light, and if it is feeding on matter, glows faintly in high-energy radiation. But there is a place around it, an invisible threshold, where the rules of movement change completely. This is the event horizon, a boundary that does not mark the surface of any object, but rather the edge of possibility itself. To understand it, imagine standing by a river with a strong current. Upstream, you can row your boat freely, choosing to drift close to the rapids or paddle away. But as you move toward the roar, there comes a point where the current is so fast that no matter how hard you row, you cannot escape being carried over the edge. In a black hole, that edge is not a waterfall, but the event horizon, and the current is not water, but the curvature of space-time itself. The event horizon is defined by escape velocity, the speed you would need to break free from the black hole's gravity. For Earth, that speed is about 11 kilometers per second. For the Sun, it is much higher. At the event horizon, the escape velocity is the speed of light. Nothing can move faster than light, and so, beyond this point, nothing can return. Not a particle, not a photon, not even a signal to say it has crossed the line. It is important to remember that the event horizon is not a wall. You would not bump into it, and it would not mark any physical change in your surroundings. If you were falling toward a black hole, the horizon would pass beneath you without the slightest ripple of sensation. You could still see the universe above you, still feel the tug of gravity just as you did a moment before. The difference would be in the geometry of your future, Every path ahead now leads inward. From the perspective of someone far away, your approach to the event horizon would look very different. To them, your motion would slow, your image fading and reddening until it became too dim to see. Time, as measured by their clock, would seem to stop for you at the horizon. But in your own experience, time would flow normally, and you would cross the boundary without pause. This is the observer paradox. The way relativity makes two equally valid, but very different stories out of the same event. Light behaves in strange ways near this threshold. Imagine a beam of light fired directly outward from just above the horizon. It will climb, but it will lose energy as it does, its wavelength stretching toward the red end of the spectrum. The closer to the horizon it begins, the more it stretches, until at the horizon itself it is infinitely redshifted and cannot escape at all. This is part of why the region just outside the horizon is sometimes called the sphere of silence, a place where light struggles and finally fails to carry messages away. If you could hover safely just above the event horizon, an impossible feat, but a useful thought experiment, you would see the universe distorted. Light from the outside world would be bent around you, magnifying the view of distant stars into a warped bright ring. Below you, the blackness would be absolute, not because it is a surface, but because it is a hole in the map of space and time, a place where every arrow of motion points inward. There is a quiet beauty to the event horizon's simplicity. It is not made of matter, yet it can be measured. It has no texture, yet it has a shape, a size, even a temperature if you consider quantum effects. It is a perfect marker. Everything that happens inside it is hidden from the rest of the universe, and everything that happens outside can, in theory, be observed. The horizon is the line between knowable and unknowable, between the places we can send our instruments and the places we can only imagine. For astrophysicists, the event horizon is not just a curiosity, it is a tool. By watching matter as it approaches and heats up, by measuring how light bends and shifts in its final moments, we can infer the size of the horizon, and from that, the mass of the black hole itself. The Event Horizon Telescope has even given us images of the shadow cast by this boundary. A glowing ring of material circling a darkness that marks where light can no longer escape. Yet for all its scientific precision, the event horizon is also a kind of poetry. It is the edge of return, the line beyond which journeys are final. It reminds us that the universe has places we cannot see, paths we cannot retrace. And still, those places are part of the same reality we inhabit. The horizon does not remove them from existence. It only places them beyond our reach. If you ever found yourself crossing it, you would not see the moment of separation. There would be no alarm, no sudden lurch. But somewhere in that crossing, your place in the universe would change forever. Behind you, the sky of distant stars would grow smaller, compressed into a shrinking circle of light. Ahead, space would curve inward, guiding you toward whatever lies in the hidden heart of the black hole. In the next part of our journey, we will move even closer, toward a region where light does not simply fail to escape, but is trapped in endless orbits, the photon sphere. It is there that we begin to see the strange beauty of black holes at their most visible, even as they remain the most secretive of cosmic objects. Just outside the event horizon, there is a place where light itself is caught in a strange compromise. It does not fall in, but neither does it escape. Instead, it loops endlessly around the black hole, tracing perfect circles through warped space. This is the photon sphere, a region where the gravity is strong enough to bend light into a closed orbit. The idea of light moving in a circle may seem odd. Light, after all, is supposed to travel in straight lines. But near a black hole, straight is not what it seems. Space is curved, and what looks to us like a loop is, for light, still the straightest possible path. It is simply that the path curves back on itself because the geometry of spacetime has been so deeply distorted. If you could stand at a safe distance and watch the photon sphere, you might see a ghostly halo. Light from the surrounding universe would pass through it, some rays being bent just enough to skim the edge, orbit once, and escape toward your eyes. Others might loop around the black hole several times before finding their way out. This repeated circling creates the illusion of a glowing ring, a boundary of light that marks the last place photons can linger without being swallowed. In reality, the photon sphere is not a solid shell. It has no walls or surface. It is simply a region defined by a particular kind of motion, the narrow band where light can follow a closed orbit. If a photon is nudged even slightly inward from this orbit, it will spiral into the event horizon. If it is pushed slightly outward, it will drift away into space. There is no stability here. The photon sphere is a precarious balance, a cosmic tightrope on which light dances for a moment before choosing a direction. When astronomers talk about the image of a black hole, they are often referring to the light shaped by this region. The Event Horizon Telescope, a network of radio dishes spread across the Earth, captured the now famous pictures of the supermassive black hole in the galaxy M87 and of Sagittarius A star, the black hole at the centre of our own Milky Way. In both images we see a dark centre, the shadow of the black hole, surrounded by a bright ring. That ring is not the event horizon itself, but the photon ring, formed by light from the hot swirling matter in the accretion disk being bent into our view. The accretion disk is a crucial part of this scene. Matter falling toward a black hole does not usually plunge straight in. It spirals, like water whirling down a drain, heating up as it collides with itself and compresses under intense gravity. In the final moments before crossing the horizon, this matter can reach temperatures of millions of degrees, glowing in X-rays and radio waves. From a distance, the light from this disk is bent and twisted by the photon sphere, creating patterns and brightness that reveal the black hole's size and spin. Sometimes the forces near the black hole do more than heat the disk. They also launch narrow, powerful jets of particles outward at nearly the speed of light. These jets can extend for thousands of light years, carrying energy far beyond the black hole's immediate neighbourhood. The exact mechanism is still not fully understood, but magnetic fields wound tight by the spinning accretion disk and the rotating space-time of the black hole seem to play a role. From certain angles, these jets are among the brightest beacons in the universe, visible across billions of light years. The photon sphere itself is a reminder that black holes are not simply dark voids. They are also lenses, bending and shaping the light from their surroundings. If you could look closely enough, you would see multiple images of the same star, its light having looped around the black hole different numbers of times before reaching you. In theory, you could see the entire universe reflected in a tiny, warped ring, a kind of cosmic funhouse mirror where every image is bent, repeated, and distorted by gravity's hand. There is something hypnotic about the thought of light trapped in this endless orbit. It is not the stillness of rest, but the stillness of perfect balance, a motion so precise it cannot last. Each photon's path is a knife edge between freedom and captivity, and no photon can stay there forever. The black hole always wins, or space eventually lets the light go. If we think about this in human terms, it becomes a quiet metaphor. There are moments in life that feel like this, balance between moving forward and being pulled back, caught in a loop that cannot last. The photon sphere is the cosmic version of such a moment, beautiful and fragile, visible only because it is temporary. The images of the photon ring remind us of something else as well. How far we have come in our ability to see the universe. A century ago, black holes were still a theoretical curiosity, their existence debated. Today, we have actual photographs, blurry, yes, but photographs nonetheless, of light shaped by their gravity. The fact that we can capture the shadow of something from which no light can escape is a testament to both the patience of science and the subtlety of the cosmos. Beyond the photon sphere, the path inward becomes final. The orbits end, the light disappears, and the only way forward is across the event horizon. In our journey, that is where we will go next, into the domain where light is no longer a messenger, where the story becomes harder to tell, and where the mystery of the black hole's core waits in the quiet. If we have been moving inward on this journey, tracing the path from collapsing star to event horizon, then what lies ahead is the deepest point of all, the singularity. At least that is what our equations tell us is there. It is a place described not by a photograph or an experiment, but by the mathematical predictions of general relativity. According to those equations, once matter has passed the event horizon, nothing can stop it from collapsing further. Gravity pulls without limit, compressing the mass into a region of zero volume and infinite density. On paper, this is a clear and simple result. In reality, it is something much stranger. Infinity in physics is rarely a sign of something physically real. More often, it is a signal that the theory you're using has been pushed past the conditions where it works. It is the way the mathematics raises its hand and says, "I cannot go any further." In this case, it means general relativity, for all its power in describing gravity, cannot tell us what actually happens at the very centre of a black hole. Think of it as trying to follow a map into an area it was never drawn to cover. You keep walking, tracing the road, until the markings fade and the paper goes blank. The blank space is not the end of the landscape. It is the end of your chart. The singularity is that blank space, a reminder that something continues beyond. But we do not yet know what it is. The clash with quantum mechanics makes the mystery sharper. General relativity describes gravity and the structure of spacetime on large scales. Stars, planets, galaxies. Quantum mechanics describes the behavior of particles and fields at the smallest scales. Atoms, photons, the vibrations of energy itself. Both theories work extraordinarily well in their own domains, but at the singularity, the extremes of density and curvature force them to meet. And there, they disagree completely. Relativity predicts a smooth, continuous collapse to a point. Quantum theory insists that matter and energy come in discrete, finite chunks, and that nothing can be smaller than certain fundamental scales. Both cannot be entirely correct in this situation. Somewhere in the overlap we expect a deeper theory, a quantum theory of gravity, to emerge, replacing the infinity in our equations with something finite, something that makes sense physically. Physicists have proposed various ways this might happen. Some imagine that the collapse stops at a certain point, perhaps when matter is compressed to the so-called Planck density, a density so high it is hard to even compare it to anything familiar. At that stage, quantum effects could push back against gravity, preventing further collapse. Others think space-time itself might have a granular texture at the smallest scales, changing how gravity works and eliminating the singularity entirely. But we must be careful here. The singularity is not a place we can visit or send a probe to study. Once anything crosses the event horizon, it is hidden from the outside universe forever. Our ideas about the singularity are built not from observation but from theory, and theory has limits. What lies there may be something we have not yet imagined at all. Still, the idea of a singularity has a certain quiet pull. It is the simplest possible end to the collapse. The entire mass of a star, or perhaps millions of stars in the case of a supermassive black hole, compressed into a point with no size. Whether or not that is what truly happens, it is the extreme that our current mathematics points toward. It is a reminder of how far the universe can stretch our understanding, and of how much remains uncharted. Sometimes I think of the singularity as less of a thing and more of a boundary in our imagination. It is the place where we can still write equations but no longer attach pictures to them. It is the point where words like inside and center start to lose their meaning, because space-time itself has been so radically altered that the everyday geometry we rely on has no foothold. If you could somehow survive the journey inward, ignoring for the moment the spaghettification and other hazards that lie ahead, you might find that approaching the singularity does not feel like moving toward a location at all. It could feel more like moving toward a time, or even toward the end of time as you experience it. The paths that lead there are not roads, but trajectories through space-time, and once you are on one, there is no turning back. Our next step will be to explore what might replace the singularity if our current theories are incomplete. There are ideas, some rooted in deep mathematics, some in speculative leaps, that imagine the core of a black hole not as an infinitely dense point, but as something stranger and perhaps more comprehensible. Each of these ideas is a kind of story about what the universe might be doing behind the veil of the event horizon. For now, we pause at this abstract edge. The infinity in the equations, the end of the map. The singularity is both a prediction and a challenge. It tells us where our knowledge stops, and it invites us to keep going anyway. When general relativity gives us a singularity, a point of infinite density and zero size, it may be telling us more about the limits of our understanding than about the true nature of reality. Physicists are rarely satisfied with infinities. In science, infinity is like a red warning light on a dashboard. It means something in the model is broken down, and so, over the years, many have tried to imagine what might exist instead of that impossible point. One possibility comes from the idea of loop quantum gravity, a theory that tries to merge the smooth curves of general relativity with the granular, discrete structure suggested by quantum mechanics. In this view, space-time itself has a smallest possible scale, the Planck length, beneath which it cannot be divided further. The collapse toward a singularity would stop before reaching infinity as the density approached the Planck limit. Instead of a point, the core would be a Planck star, a region of incredibly compressed matter where quantum pressure resists gravity's pull. Over unimaginable stretches of time, it might even expand again, releasing the trapped contents back into the universe in a final faint burst. Another idea comes from string theory, which replaces the notion of point-like particles with tiny, vibrating strings of energy. According to one branch of this theory, black holes are not smooth spheres with a hidden singularity at the centre, but are instead composed entirely of tangled strings. These configurations are called fuzzballs. From a distance, a fuzzball looks and behaves like a black hole. But inside there is no point of infinite density, just a dense, chaotic tangle of quantum threads. The event horizon is no longer a sharp boundary, but a fuzzy surface where these strings interact with the outside world, potentially preserving information that would otherwise be lost. There is also the more exotic notion of the gravastar, short for gravitational vacuum star. In this model, the collapse of a massive star does not form a singularity at all. Instead, the outer shell of matter is held in place by an interior filled with dark energy, the mysterious force driving the accelerated expansion of the universe. The surface of a gravastar would hover just outside where the event horizon would have been, creating an object that mimics many of the behaviours of a black hole without hiding a singularity inside. The idea is speculative, but it offers an intriguing way to sidestep the problem of infinity. And then there is perhaps the most romantic of possibilities, that the centre of a black hole might be a bridge to another universe. This idea traces back to Einstein and Rosen, who in 1935 described a mathematical solution to general relativity that connected two regions of space-time through a tunnel, what we now call a wormhole. In theory, the core of a black hole could lead somewhere else entirely, with matter and light falling in on one side and emerging in another part of the universe, or even in a completely separate universe. In practice, such a wormhole would be unstable, collapsing faster than anything could pass through. Still, the thought that a black hole might be not an ending but a doorway is hard to resist. Each of these models tries to answer the same question. What happens to matter and energy when they are pushed beyond the limits we can test? The answers differ, but they share a certain optimism. They suggest that perhaps nothing is truly destroyed, that the information carried by the things that fall into a black hole may still exist in some form, woven into the structure of whatever lies at its heart. The truth is that we do not yet know which, if any, of these ideas is correct. Observations of black holes are still limited to their effects on their surroundings, the light from their accretion disks, the ripples of gravitational waves from their mergers, the shadows captured by radio telescopes. None of these yet reveal what lies beyond the event horizon, and yet exploring these possibilities is valuable because it reminds us that the singularity is not the end of the story, only the end of the part we can currently tell with confidence. Speculative as they are, these models change how we might think about black holes. A Planck star would eventually release its contents back into the cosmos. A fuzzball would have no hidden core, only a tangled mass of quantum strings that might encode the past. A gravastar would be an entirely different kind of object, one that blurs the line between star and vacuum. A wormhole could make a black hole not a tomb but a bridge. For now, these are sketches in the margins of our cosmic map, drawn with the hope that one day better observations or deeper theories will fill them in. Whether the truth turns out to be one of these, a combination of them, or something we have not yet imagined, it will almost certainly tell us something new about the nature of space, time, and the limits of the possible. In the next part of our journey, we will leave theory behind for a while and imagine what it might feel like to approach the core ourselves. We will step across the event horizon in thought, drift past the photon sphere and begin the long fall inward. It will be a fall that stretches and distorts, where the pull of gravity changes not just where you are but how you experience time itself. The journey will be impossible to survive in reality, but here we can follow it as far as imagination allows. If we imagine stepping across the event horizon and drifting inward, the first thing to understand is that the pull of gravity here is not uniform. It is not like the steady, even attraction we feel on Earth, where gravity at your head is almost exactly the same as gravity at your feet. Inside a black hole, the gradient, the difference in gravitational pull from one point to another, grows enormous. And it is this difference that shapes the experience of falling. The effect has a name that sounds almost whimsical: Spaghettification. It describes what happens when one part of an object is pulled harder than another. If your feet are closer to the core, they feel a stronger pull than your head. The result is stretching along your length and compression across your width, turning you into a thinner and thinner strand. The name is playful, but the reality is not. This stretching would happen to anything: a spacecraft, a planet, a cloud of dust. Caught in the extreme tidal forces near a black hole, the intensity of spaghettification depends on the size of the black hole. For a small stellar mass black hole only a few times the mass of the Sun, the gradient becomes deadly well before you even reach the event horizon. The difference in pull between head and feet is so extreme that nothing can withstand it. The fall is short and violent, ending in a fraction of a second. But for a supermassive black hole, the story changes. The event horizon is much farther from the centre, and the gravitational gradient there is gentler. You could cross the horizon without noticing anything unusual. No sudden pull, no tearing. The stretching would only become noticeable much deeper in, perhaps close to whatever lies at the core. This means that, at least in theory, you could fall quite far before the tidal forces became overwhelming. From the perspective of an outside observer, your fall would look frozen. The light you emit would be stretched into longer and longer wavelengths, fading from visible colours into deep red, then into infrared, then into radio waves too faint to detect. But from your perspective, the fall continues smoothly. The blackness ahead does not look like a wall, but like an open sky without stars, a place where the geometry of space curves so steeply that every possible path leads inward. As you fall closer, the stretching becomes not just a sensation, but a transformation. Your body, and any matter, is made up of atoms, each held together by electromagnetic forces. The tidal forces begin to overpower those bonds, pulling the atoms apart. Protons and neutrons, themselves bound by the strong nuclear force, would hold on longer, but even they would eventually feel the strain. The forces here are not subtle. They are patient but irresistible, unfolding over distances that shrink rapidly as you near the core. In smaller black holes, this process is abrupt. You would not have time to register much beyond the growing pull before the forces reached levels no structure could survive. In larger ones, it is drawn out, almost deceptive in its slowness. You could drift inward for minutes, hours, perhaps longer, as the light from the outside universe grows smaller and dimmer, compressed into a shrinking patch of sky. And then, perhaps without a clear moment of transition, you would find that up and down have lost their meaning. Directions themselves begin to blur. In normal space, you can orient yourself by looking toward or away from a source of gravity. But here, the curvature of space-time is so extreme that every direction points inward. It is not a tunnel in the way we think of tunnels. It is more like a slope that steepens everywhere at once. The concept of spaghettification can sound like something from a comic book, a bit of exaggerated imagery to make black holes sound more dangerous. But it is simply the natural consequence of gravity's rules. The greater the difference in distance between 2 points, the greater the difference in the pull they feel. And near a black hole, that difference can grow to the point where even the fabric of matter unravels. Still, there is something oddly serene in imagining this from the safety of thought. To be stretched into a line is, in a way, to be aligned completely with the pull of the universe's most extreme object. You're no longer a shape resisting its environment, but part of a single motion toward the deepest curve in space-time. From here, our path inward is no longer about surviving, but about experiencing what such a fall might mean for time and perception. Because as gravity grows stronger, time itself begins to flow differently. The clocks you carry, whether mechanical, electronic, or simply the rhythm of your own heartbeat, will not match those in the outside universe. And that mismatch will not just be a number in an equation. It will change the way you feel the moments passing, until the idea of passing itself becomes uncertain. That is where we will go next, into the strange space where direction fades, time stretches, and the fall is less about distance than about the changing shape of reality itself. If the fall toward the heart of a black hole begins as something you can imagine in terms of movement, a downward pull, a shrinking sky, there comes a point when those familiar anchors dissolve. It is not sudden, like stepping off a ledge, but gradual, like watching fog erase the edges of a landscape. The difference is that here, it is not sight that fails first, but the very structure of space and time around you. In ordinary life, direction is simple. You can point toward a place and say, there, and point toward another and say, back. Inside a black hole, those designations become meaningless. Every direction, no matter how you turn, leads inward. There is no away from the core, only paths that curve toward it. Even the concept of falling starts to lose its shape. Falling implies a surface to reach, a place to stop, but in here, movement is less about travelling through space and more about moving through a changing geometry that offers no final platform to land on. Time begins to shift under you as well. In the outside universe, someone watching your fall would see you slow, dim, and fade, as if time for you were grinding almost to a halt. They would never see you cross the horizon. To them, you would be frozen in place, stretched into an image that becomes redder and fainter until it disappears. But for you, The moments would continue in a steady, uninterrupted flow. You would cross the horizon without noticing the instant, and time for you would carry on, one heartbeat after another. As you move inward, the distortion of time becomes something you might feel in your bones, though not in the way we sense time in daily life. Clocks and watches, if you had them, would keep perfect pace with your heartbeat, with the rhythm of your thoughts. But compared to the outside, those same clocks would seem to run infinitely slow. You could, in theory, see the outside universe accelerate. Stars shifting, galaxies drifting, whole epochs passing in what for you might be minutes. Light from distant places would pour in, compressed in frequency, so that the history of the universe could flash past your eyes in a torrent too fast to comprehend. This effect is not magic. It is the result of how gravity bends space-time. The stronger the gravity, the more it slows the flow of time relative to regions with weaker gravity. Near the core, the curvature is so extreme that this difference is no longer a matter of seconds or years, but of cosmic ages. The same laws that slow you to a stop in an outside observer's view also give you the possibility, at least in theory, of glimpsing vast stretches of cosmic history in the blink of your own experience. But there is a limit to what you could make sense of. Your mind is built to process events at a human pace, the turn of the earth into day and night, the slow unfolding of a conversation, the rising and setting of seasons. To have the evolution of galaxies compressed into moments would be like trying to read a library's worth of books by glimpsing the spines as they rush past at the speed of light. You might catch a pattern, a blur of change, but the details would vanish in the flood. Direction fades not only because every path points inward, but because the shape of space itself changes in ways we cannot directly imagine. In our everyday geometry, you can trace a straight line and be confident it will remain straight. Here, straight lines curve back, and the coordinates you might have used to describe a location twist into something unrecognizable. The place you're falling toward is not so much ahead as it is everywhere you're going. It is less like a destination and more like a condition you're moving into. If you tried to navigate in such a place, you would have nothing to orient by. No stars, no horizon, no steady point of reference. The light that reaches you has been bent and redirected so many times that it no longer marks the true positions of the objects it came from. You would be surrounded not by a clear view of space, but by a shifting, warped panorama that defies any attempt to tell where out there really is. There is a quiet disorientation in imagining this. The absence of direction is not chaos, but a kind of order you're unused to, an order in which every path is the same, every choice leads to the same place. In such a geometry, movement is not escape, and stillness is not rest. Everything is part of the same inward curve. Time, too, loses its usual role as a marker of change. It becomes elastic, stretching and bending under the weight of gravity. For you, the seconds might feel perfectly normal, but if you could compare them to the seconds of someone outside, you would find they no longer match. Your seconds might contain years, centuries, even millennia of theirs. And yet, you would not feel this difference. You would simply live your moments as you always have, unaware that outside the universe is rushing forward without you. If there is a poetry to this, it is a strange one. To be in a place where direction is gone and time is no longer shared with the rest of the cosmos is to be cut off in a way that no journey across ordinary space could ever accomplish. You're still part of the universe, but the link between your clock and everyone else's has been severed. In a way, you have stepped out of the common flow of time into a private stream that runs only one way, toward a place we cannot yet describe. And that is where our path will take us next, deeper into the interior, toward the heart of the mystery, where our theories falter and only speculation remains. So far, we have spoken of black holes as if they were perfectly still, dark, motionless spheres, pulling everything inward with equal force in all directions. But in the real universe, perfection is rare. Stars spin, clouds of gas swirl, galaxies rotate, and when a star collapses into a black hole, or when a black hole grows by swallowing matter, that rotation is carried into the new form. The result is a rotating black hole, what physicists call a Kerr black hole. Rotation changes the story. It changes the shape of spacetime itself. A non-rotating black hole curves space as if pressing a perfect symmetrical dent into the cosmic fabric. A rotating black hole twists that fabric as well, dragging it around in the direction of its spin. This is frame dragging, and it is not just a poetic image but a physical reality. Space and time themselves are pulled along with the rotation. Imagine placing a spoon into a cup of thick honey and slowly twisting it. The honey does not stay still while the spoon moves. The whole liquid begins to swirl, carrying anything inside with it. Frame dragging is like that, except the honey is space-time, and the spoon is the black hole's mass and spin. Anything near it, particles, light, even the empty space, is caught in the rotation. For an object like Earth, which spins far more gently than a black hole, frame dragging is almost imperceptible. Satellites can measure it, but it is a tiny effect. Near a Kerr black hole, the effect becomes profound. The closer you get, the harder it becomes to resist being pulled along. Even light cannot hold its ground. Its path curves with the spinning geometry. If you were to hover close enough, assuming you had a way to resist gravity's pull, you would find that standing still relative to the distant stars is impossible. Space-time itself is moving beneath you. This twisting of space-time also changes the event horizon. In a non-rotating black hole, the horizon is perfectly spherical. In a Kerr black hole, it flattens slightly at the poles, bulging outward at the equator where the spin is greatest. Just outside this horizon lies something new, a region that does not exist in the still Schwarzschild case. It is called the ergosphere, and it will be the focus of our next session. But before we get there, it is worth pausing to imagine what this rotation means for anything falling in. If you approach the black hole from the direction opposite its spin, you would be fighting not just gravity, but the momentum of space-time's twist. Your path inward would be slower, your resistance harder. If you approach from the same direction as the spin, you would be helped along, almost as if the black hole were reaching out to sweep you in with a turning arm. Rotation also affects what happens outside the immediate neighbourhood of the hole. The accretion disk, that bright hot ring of matter swirling in, is shaped and heated by the spin. A fast-spinning black hole can drag material in closer before it disappears, increasing the amount of energy released in the process. The hotter the material gets, the more light it produces, and the more clearly we can see it from across space. Jets, those narrow, powerful streams of particles that shoot out from near the poles, may also be powered, at least in part, by the rotation. Magnetic fields wound tight by the spinning disk, and space-time itself can fling material outward at nearly the speed of light, sending a signal across millions of light-years that here, in this galaxy, a giant is feeding. The mathematics describing a Kerr black hole is precise, but you do not need the equations to sense its strangeness. It is enough to picture space as something that can be set in motion, turning without friction, pulling even light into its swirl. In that sense, a rotating black hole is not just an object, it is a place where the very stage of the universe spins. There is also something humbling in this. The rotation of a black hole can last for billions of years, almost unchanged. Once it is set spinning, there is nothing to slow it down, no air to create drag, no surface to generate friction. Unless it interacts with other massive objects or loses angular momentum through complex processes near its horizon, it will keep turning long after the stars that once circled it are gone. When we think of rotation in our own lives, it is often in terms of cycles we can see, the turning of Earth bringing day and night, the seasons shifting as our planet loops around the sun. In the scale of black holes, rotation is not a short cycle, but an enduring characteristic written into the geometry of space-time itself. It is a reminder that motion once given can be as permanent as the void. From here, our path will take us closer to that strange new region carved out by the spin, the ergosphere, where standing still is impossible, and where, at least in theory, the energy of the black hole's rotation can be tapped. It is one of the rare places in the universe where you can take from gravity itself, and it exists only because of the twisting fabric of space. When a black hole spins, it does more than twist the fabric of space. It creates a zone outside its event horizon, where the rotation is so intense that nothing can remain still with respect to the distant universe. This region is called the ergosphere, and its very name suggests a place where energy might be drawn from, ergo meaning work. The ergosphere is shaped like a flattened sphere, bulging at the equator and narrowing toward the poles. It lies between the event horizon and the outer boundary, where space-time is dragged faster than light could remain stationary. In everyday life, we think of space as something fixed, something that objects move through. Here, space itself is in motion, and everything within this boundary is swept along. Even light cannot hold its position relative to distant stars. It is carried around the black hole like leaves in a swirling current. If you were to enter the ergosphere, you would not necessarily be doomed to cross the event horizon. The ergosphere is outside that ultimate boundary, so with the right trajectory, you could still escape. But you would have no choice about rotating with the black hole. The fabric of space-time itself is turning, and you are a passenger. It would be as if you were standing on the surface of the Earth at the equator. You cannot stand still relative to the sun because the planet carries you eastward, whether you wish it or not. Here, the planet is space-time, and its rotation is far more extreme. This unique environment led physicist Roger Penrose in 1969 to imagine a way to extract energy from a rotating black hole. The idea, now called the Penrose process, works like this. If you send an object into the ergosphere and split it into two pieces, you can arrange it so that one piece falls into the black hole and the other escapes. Because of the way energy and momentum work in the twisted space-time, the piece that escapes can leave with more energy than the original object had when it entered. The extra energy comes from the black hole's rotation, which slows slightly as a result. The effect is not magic. It is simply the conservation of energy playing out in a place where the rules of motion are reshaped by gravity's spin. In theory, you could repeat the process over and over, gradually draining the rotational energy of the black hole. The total amount available is vast. For a maximally rotating black hole, it could be nearly 30% of its mass energy, a number that dwarfs anything achievable with chemical or nuclear fuel. Of course, in practice, the Penrose process is extraordinarily difficult to carry out. It would require precise control over the trajectories of particles in a region where gravity is extreme and space-time is warped in complex ways. But the principle is more than a curiosity. It has inspired other ideas, such as mechanisms for powering the enormous jets of plasma we see shooting from the poles of active galaxies. In some models, magnetic fields anchored in the spinning accretion disk act like cosmic flywheels, drawing rotational energy from the black hole in a manner not unlike the Penrose process. Standing in the ergosphere, if standing is even the right word, would be like being caught in a slow but irresistible whirlpool, one that carries everything along not through a fluid, but through the structure of the universe itself. You could still, with effort, move outward and escape, but never without turning. The rotation is not something you can opt out of. It is built into the coordinates of space and time in this region. There is a certain elegance to the ergosphere's existence. In most places in the cosmos, extracting energy means consuming something, burning fuel, splitting atoms, annihilating particles. Here, you can take from motion itself, without destroying the object in the process. The black hole remains, turning a little more slowly each time, but still whole. If the universe were a vast ancient machine, the ergosphere would be one of the few places where you could insert a lever and draw power directly from its moving parts. Even though no spacecraft has ventured near a black hole, we have indirect hints of similar processes playing out on cosmic scales. The enormous luminosities of quasars, the immense power of relativistic jets, and the shaping of galaxy clusters by active black holes may all involve the transfer of rotational energy from black holes to their surroundings. The ergosphere, invisible to the eye, may be the hidden stage on which these colossal exchanges of energy take place. And yet, as we leave this region in thought and continue our journey outward in scope, it is worth remembering how fragile our understanding still is. The ergosphere is not a place we can map in detail from observation. We know it through equations, through the consistency of predictions with what little we can measure. To truly understand it, we would need to approach it, and in reality, that is something we may never do. For now, the ergosphere remains a reminder of how rotation transforms gravity's role. It is not only a force pulling inward, it can also be a storehouse of energy, a resource written into the shape of space-time itself. In the next stage of our journey, we will step back from this close encounter and look at black holes not as destinations, but as central figures in the lives of galaxies, anchors, engines, and in some cases lighthouses shining across the dark. So far, we've imagined black holes as solitary travellers, the remnants of dying stars, small enough to cross in a heartbeat and hidden away in darkness unless they're feeding. But there is another kind of black hole, far larger and more influential, and these do not wander alone. They sit at the hearts of galaxies, vast beyond measure, with masses millions or even billions of times that of our Sun. We call them supermassive black holes, and in a way they are the silent anchors around which entire galaxies turn. The nearest one to us, at least in cosmic terms, is Sagittarius A star, resting at the centre of the Milky Way. It lies some 26,000 light-years away in the direction of the constellation Sagittarius, hidden behind clouds of gas and dust. We cannot see it directly, but we can watch the stars that circle it. Over the years, astronomers have traced the orbits of these stars, some moving at thousands of kilometres per second, as if whipped around by an invisible tether. By measuring these orbits, we know the mass. At the centre, about 4 million suns worth, confined to a space smaller than our solar system. Nothing we know of, except a black hole, could pack such mass into such a small volume. And then there is M87 star, the supermassive black hole in the giant elliptical galaxy Messier 87. It is over 6 billion times the mass of the Sun. This was the black hole whose shadow was first imaged by the Event Horizon Telescope in 2019. That faint glowing ring of light surrounding a dark centre. The photograph travelled across news headlines, not because it was beautiful in the usual sense, but because it was the first time humanity had seen the silhouette of one of these giants. Supermassive black holes are not simply oversized versions of the stellar black holes we have already discussed. They may have formed in different ways, perhaps from the collapse of massive clouds of gas in the early universe, or through the merger of many smaller black holes over time. However they were born, once they are in place, they become gravitational centres around which their galaxies organise themselves. The connection between a galaxy and its central black hole is more than just location. Observations show that the mass of a supermassive black hole is closely related to the mass of the galaxy's central bulge of stars. This is the M-sigma relation, and it suggests that the growth of the black hole and the growth of the galaxy are linked. Somehow they regulate each other, as if engaged in a slow and ancient conversation. When a supermassive black hole is feeding, it can release enormous amounts of energy. Matter falling toward it forms an accretion disk, heated to such high temperatures that it glows with fierce brightness. This energy can push back on the surrounding gas, driving powerful winds that sweep through the galaxy. Such feedback can suppress the formation of new stars by blowing away the raw material they would have formed from. In other cases, it may compress gas clouds, triggering bursts of star formation. This means that the quiet giant at a galaxy's centre is not always so quiet. It can act as a kind of cosmic thermostat, controlling the pace at which its galaxy forms stars, shaping its evolution over billions of years. Without these central black holes, galaxies might look very different. Even when dormant, a supermassive black hole exerts a profound influence. Its gravity helps hold the inner galaxy together. Stars in the central regions move under its pull, their orbits shaped by the invisible mass. It is a reminder that gravity does not have to be dramatic to be important. It can work slowly, steadily, over spans of time so long that no single generation of stars would notice the change. From a human perspective, these objects are impossibly remote and unapproachable. Yet they are also intimately connected to us. The Milky Way's own history, the rate at which it formed stars, the way its spiral arms grew, even the distribution of heavy elements in its disk, has been influenced by Sagittarius A star. Our Sun formed in a galaxy already shaped by its central black hole, and our planet, our oceans, and our bodies carry the fingerprints of that history. When we look up at the night sky and see the faint band of the Milky Way stretching across it, we are seeing the thin disk of our galaxy from the inside. Every star in that arc orbits around the galactic centre, and at the very core of that motion lies a dark, massive presence that has been there for most of the universe's age. We orbit it without thinking, carried along in a dance so vast we can barely imagine its scale. From here, our path will take us to the most brilliant of the black hole's moods, the quasar phase, when a supermassive black hole feeds so rapidly that it outshines its entire galaxy. These are the beacons we can see from across billions of light years, their light reaching us from an era when the universe was young. If a supermassive black hole at the centre of a galaxy is quietly feeding, its influence can be subtle, regulating star formation, shaping the orbits of nearby stars, and gently holding the galaxy's structure together. But when that feeding becomes intense, the quiet giant transforms. The surrounding gas and dust rush inward in torrents, forming an accretion disk so hot and bright that it can outshine every star in the galaxy combined. In this state, the black hole is no longer a hidden anchor. It becomes a beacon visible across the cosmos, what we call a quasar. The word quasar comes from quasi-stellar radio source, a name coined in the 1960s when astronomers first detected these mysterious points of light. Through early telescopes they looked like faint stars, but their spectra and radio emissions told a different story. They were too bright, too distant, and too energetic to be ordinary stars. As our understanding grew, it became clear. Quasars are the blazing hearts of galaxies, powered by supermassive black holes consuming matter at extraordinary rates. A quasar's light comes from the accretion disk, matter swirling around the black hole, heated by friction and gravitational compression to temperatures of millions of degrees. This light is not just visible. It spans the electromagnetic spectrum from radio waves to X-rays. Some quasars emit jets, narrow beams of particles launched at nearly the speed of light from the regions near the black hole's poles. These jets can stretch for millions of light years, punching through intergalactic space like luminous arrows. The energy output of a quasar is staggering. A single one can shine with the power of 1 trillion suns. And because light travels at a finite speed, when we see them, we are looking back in time, often to an era when the universe was less than a quarter of its current age. Quasars tell us about the early growth of galaxies, about how matter first gathered in large structures after the Big Bang. Despite their brilliance, quasars do not last forever. They are a phase in the life of a galaxy, triggered when enough gas and dust fall toward the central black hole to ignite such intense activity. This can happen after galaxy mergers, when gravitational tides funnel material toward the center. Once the black hole has consumed or blown away the nearby gas, the accretion slows, the light dims, and the quasar fades into a quiet, dormant state. The black hole remains, but its voice becomes a whisper instead of a roar. Quasars also shape their host galaxies in profound ways. The winds and radiation they emit can sweep through the galaxy, heating and dispersing the interstellar medium. This feedback can shut down star formation, locking the galaxy into a mature, stable form. In other cases, the same processes may compress clouds of gas, triggering bursts of new stars. The interplay is delicate, and each galaxy's history is shaped by how its central black hole feeds and rests over billions of years. From Earth, we study quasars through light that has travelled for billions of years to reach us. It is strange to think that when that light set out, our planet was not yet formed. The sun had not yet been born, and the Milky Way itself was still assembling its spiral arms. The photons that now enter our telescopes began their journey before life's first stirrings in our corner of the cosmos. They are messengers from a time when the universe was denser, younger, and more active, carrying the signatures of matter spiraling into some of the most powerful engines ever known. And yet, for all their enormity, quasars remind us that black holes, even the largest ones, are not purely destructive. In their brightest phase, they are creators of change, shapers of galaxies, and markers of cosmic history. Without them, the distribution of stars, the chemistry of galaxies, and perhaps even the timing of life's emergence in the universe might have been different. To the human eye, trained to seek meaning in light, quasars are paradoxical. They are born of darkness, yet they blaze with unmatched brilliance. They are powered by the consumption of matter, yet their energy travels outward across the void, touching places that will never feel the black hole's pull. In a way, they are the universe's way of announcing its own hidden forces, the buried giants that reveal themselves only when fed. From here, our journey will turn again. We will leave the blazing light of the quasar and return to something quieter but equally profound, the ripples that black holes can send across the fabric of space-time itself. These are gravitational waves, the subtle luster tremors of the universe, carrying news of events that happen in regions where even light cannot escape. They are the faintest of whispers, and yet they can be heard across billions of light years. Black holes are often imagined as solitary hunters, drifting through the galaxy in quiet isolation. But in reality, many are born as pairs. They begin life as massive stars formed in the same cloud, orbiting one another in a slow, steady dance. Each star evolves, burns through its fuel, and eventually collapses. First one becomes a black hole, then the other. What remains are two dark objects locked in a gravitational embrace, orbiting around a shared center, bound together by a force they can never escape. For millions, sometimes billions of years, the pair continues its silent waltz. Each orbit is almost identical to the last, a pattern repeating in deep time. But with every turn they lose an almost imperceptible amount of energy. This loss does not come in the form of light, for black holes emit none. Instead, it leaves as gravitational waves, ripples in the very fabric of space-time spreading outward in all directions. Einstein predicted these waves in 1916, but for a century they remained undetected. The ripples are unimaginably small, distorting space by a fraction of a proton's width, even after travelling across hundreds of millions of light years. And yet, with each orbit, more energy is carried away. The black holes spiral closer, the dance becomes faster, the steps shorter. As the distance between them shrinks, their orbital speed climbs. Near the end, they may be circling each other dozens of times per second. The energy pouring into gravitational waves grows exponentially. In the last moments before collision, they are moving at a significant fraction of the speed of light. their combined gravity twisting space-time so violently that the ripples are no longer whispers. They are the loudest signals the universe can send without using light. And then the moment comes. The two horizons touch. The black holes merge into one, larger and more massive than either alone, though slightly lighter than the total sum of their masses. That missing fraction, a few suns worth of matter, has been converted entirely into gravitational waves, radiating outward in a final resonant burst. The newborn black hole quivers, just for a heartbeat of cosmic time, then settles into a perfect silent sphere. On Earth, this drama passes unnoticed to human senses. But far from the galaxies where these mergers occur, we have built instruments to feel them. The Laser Interferometer, Gravitational Wave Observatory, LIGO, consists of two enormous L-shaped detectors, one in Louisiana and one in Washington state. Each arm stretches for kilometers, and inside them, lasers bounce back and forth between mirrors, measuring the distance with exquisite precision. On September 14th, 2015, a signal arrived almost simultaneously at both sites. It lasted just a fraction of a second, a rising tone like the brief chirp of a bird. This was GW150914, the first confirmed detection of gravitational waves. It came from two black holes, each about 30 times the mass of the Sun, merging over 1 billion light-years away. The event released more energy in gravitational waves in that brief moment than all the stars in the observable universe emit as light over these arms' span of time. It was a moment of scientific history. For the first time, we had directly detected not just light or particles from the cosmos, but the shifting of space-time itself. We were no longer only seeing the universe, we were listening to it. Since then, LIGO, joined by the Virgo detector in Italy, and later by KAGRA in Japan, has recorded dozens of such mergers. Each one is a different story, sometimes two black holes, sometimes two neutron stars, and in rare cases, one of each. Each event carries unique information about the masses of the objects, their spins, the distance to their collision, and the universe's expansion. Black hole mergers are not rare in the cosmos, but they are fleeting. The final seconds of their dance are the only time they can truly be noticed, and only by instruments sensitive enough to detect the faint tremors they send through space-time. The rest of their lives are spent in deep obscurity, invisible except for their gravitational pull. In a sense, the dance of death is an imperfect name. For the black holes themselves, the merger is not an end but a transformation. They do not vanish, they become one. The death is only of the binary system, the pairing that had defined their existence for eons. The new black hole carries forward the combined mass, the combined spin, and perhaps traces of the history written into the fabric around it. When we detect such an event, we are hearing something that happened long ago in a place we can never visit. By the time the waves reach us, the merged black hole has long settled into silence. The light from the galaxies where these mergers occurred is often too faint for our telescopes to see. Yet the waves arrive, unweakened by dust or gas, unaffected by the obstacles that block light. They are messengers that slip through the universe's barriers, carrying news of places otherwise unreachable. It is humbling to think that these signals travel for billions of years, only to nudge our detectors by less than the width of an atomic nucleus. And yet, with that tiny motion, they tell us stories of unimaginable violence, beauty, and scale. They show us that even in the universe's deepest shadows, there is motion, rhythm, and the potential for connection. In our next step, we will explore what it means to listen to the darkness, how gravitational waves have opened a new window on the cosmos, letting us hear events in places light will never reach, and giving us a deeper understanding of the hidden, moving universe. Before gravitational waves, our entire view of the universe depended on light. From the earliest naked eye observations to the most advanced space telescopes, astronomy has always meant collecting photons, the particles of light that travel across space and carry with them the imprint of the objects they left behind. We have learned to see in many kinds of light, from radio waves with their long, rolling crests to gamma rays with their fierce, tiny oscillations. Yet for all its range, light can only tell us so much. It can be absorbed, scattered, or blocked entirely. There are regions of the cosmos, dense stellar interiors, the very moment of the Big Bang, the heart of a black hole merger, where light cannot escape at all. Gravitational waves are different. They are not particles travelling through space. They are distortions of space itself, rippling outward from their source. Imagine stretching a sheet of fabric taut, then tapping it gently in one spot. The vibration moves through the cloth, and the fibres themselves shift and return. In the same way, when massive objects accelerate, two black holes spiralling together, two neutron stars colliding, they send ripples through the fabric of space-time. Those ripples travel without being stopped by matter. They pass straight through stars, galaxies, even us, without slowing down. The beauty of gravitational waves is not only in what they are, but in what they can reveal. Light can be trapped, but gravity cannot be hidden. A black hole merger, invisible in every wavelength, still sends out waves that race across the universe at the speed of light, announcing an event that would otherwise remain secret. With gravitational wave astronomy, we're no longer limited to what shines. We can detect what moves. When the first detection was made in 2015, it was as though a new sense had awakened. We'd been looking at the cosmos for millennia. Now we could also listen. The data from LIGO and Virgo do not arrive as sound, but as patterns in the stretching and squeezing of space. Yet when translated into audio frequencies, these patterns can be heard. The signal from a black hole merger rises in pitch and amplitude as the orbit tightens. A quick, sliding tone, ending in a sharp cut-off when the merger is complete. The universe's deepest events become brief songs, each with its own shape and story. Listening in this way has already led to discoveries that light alone could not provide. We have confirmed that black hole binaries exist in large numbers, in a range of masses and spins. We have measured the collision of neutron stars, events that also produce light, and have been able to match gravitational and electromagnetic signals to pinpoint their location in the sky. This combination, light and gravity together, gives us a fuller, richer view of astrophysical events, like seeing a scene while also hearing its soundtrack. Perhaps most profound is the idea that gravitational waves let us look further back in time than light ever could. The earliest light we can see comes from about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely. Before that, the cosmos was opaque to light, but gravitational. Waves could have travelled freely even in those first instants, carrying information from a time when the universe was only seconds old. If we can detect waves from that era, we might glimpse the very moment when space and time themselves began to stretch. For now, our instruments are tuned to events involving stellar mass and intermediate mass black holes, neutron stars, and perhaps in the future, supermassive black hole mergers. But even this first step into gravitational wave astronomy feels like standing on the shore of a vast new ocean. Every detection is a message from a place light cannot reach. Every signal adds to our growing map of the hidden universe. There is also a poetic symmetry in the fact that these waves, born in the most violent events the cosmos can produce, arrive here so gently. They do not scorch our detectors with radiation. They do not knock atoms apart or blast away atmospheres. They simply pass through, shifting distances by a tiny fraction, then moving on. It is as if the universe has chosen to whisper its most intimate stories, knowing they will be heard only by those patient enough to listen. In time, as detectors grow more sensitive, we may be able to catch the faint hum of countless unresolved signals, a background of gravitational waves from all the mergers that have ever happened. It would be the gravitational equivalent of the cosmic microwave background, the afterglow of the early universe, but woven from ripples instead of photons. Listening to that background would be like hearing the collective heartbeat of the cosmos across billions of years. From here, our journey will shift again, moving from the motion and sound of black holes to their deeper, quieter nature as thermodynamic objects. Things with temperature, entropy, and a strange set of laws that blur the line between gravity, quantum mechanics, and heat. In the next step, we will see that a black hole is not only a shadow in space, but also a kind of cosmic engine with rules as fundamental as the laws of motion themselves. For most of our journey so far, we have spoken of black holes in terms of gravity, their pull, their influence, the way they shape light and matter. But black holes are not only gravitational objects, they also obey laws that sound, at first, as if they belong to a completely different realm of physics, the laws of thermodynamics. These are the same principles that govern how heat flows, how engines work, and why a cup of coffee cools down on your desk. It turns out that a black hole, in its own strange way, is a thermodynamic system, and understanding this changes how we see both black holes and the universe itself. In the early 1970s, physicists began to notice parallels between the mathematics of black holes and the mathematics of heat and energy. Stephen Hawking, Jacob Bekenstein, James Bardeen, and others realized that you could write down laws of black hole mechanics that looked almost exactly like the familiar laws of thermodynamics. At first, many thought it was just an analogy, a curious similarity but not a literal truth. After all, a black hole was supposed to be completely black, with no temperature at all. What heat could it possibly have? The zeroth law of thermodynamics says that if two systems are in thermal contact and at equilibrium, their temperatures are the same everywhere. In a black hole, the analogue is that the surface gravity, the gravitational acceleration felt at the horizon, is constant across the entire event horizon, no matter where you measure it. This surface gravity acts like temperature in the analogy. The first law of thermodynamics says that energy is conserved. You can't create or destroy energy, only transform it. In black hole terms, the total energy of the black hole, its mass energy, changes when you add matter or energy. But this change is related to the change in the area of its event horizon, its rotation, and its electric charge. Drop something into a black hole and its mass increases, and so does the size of its horizon. The second law of thermodynamics says that entropy, a measure of disorder or information content, never decreases in an isolated system. Bekenstein proposed that a black hole has an entropy proportional to the area of its event horizon. This means that when matter falls in, the horizon's area, and therefore the entropy, always increases. It is as if the black hole's surface is a vast ledger, recording everything that has ever crossed the boundary, even if that information is scrambled beyond recognition. The third law of thermodynamics says that you cannot reach absolute zero temperature in a finite number of steps. For black holes, the analogue is that you cannot reduce a black hole's surface gravity to zero by any finite process. There is always a limit, a kind of cosmic minimum that prevents you from creating a perfectly cold black hole in the mechanical sense. For a time, these parallels seemed purely formal. Black holes, after all, were thought to have zero temperature, perfect absorbers that emitted nothing. But in 1974, Hawking made a discovery that would transform the analogy into reality. Black holes do have a temperature, and they do emit radiation. That story belongs to the next part of our journey, but it means that these laws are not just mathematical coincidences, they are physical truths. The most surprising of all is the temperature of a black hole. The formula shows that a black hole's temperature is inversely proportional to its mass. This means the bigger the black hole, the colder it is. A stellar mass black hole might have a temperature of less than a millionth of a degree above absolute zero. A supermassive black hole could be colder than the cosmic microwave background, colder than the faint afterglow of the Big Bang itself. It feels strange to think of such an extreme object as cold. In popular images, black holes are surrounded by blazing disks of matter, glowing in X-rays with jets of plasma shooting into space. But that heat is not from the black hole itself. It comes from matter falling in, heating up as it is torn apart. The black hole's own temperature is almost unimaginably low. In a sense, a black hole is the coldest kind of heat you can imagine, one that holds its energy in a form you cannot touch, see, or release, without changing the fabric of space itself. There is also something deeply poetic in the fact that a black hole's entropy is tied to the area of its horizon, not its volume. In the everyday world, the amount of disorder or information you can store depends on the space inside a system, but for black holes, it is the surface that counts. This idea, that the maximum information content of a region is proportional to its boundary area, would inspire the holographic principle, a radical concept suggesting that the universe itself might be describable as information written on a surface. Black hole thermodynamics blurs the boundaries between gravity, quantum theory, and thermodynamics, three great pillars of physics that are usually studied separately. In the strange extreme conditions near an event horizon, these pillars lean toward each other, and their intersection might be the place where the deepest truths about the universe hide. In the next part of our journey, we'll see how Hawking's discovery of black hole radiation connects all these ideas, turning what seemed like a cold and eternal shadow into something that slowly, patiently, fades away over unimaginable timescales. In 1974, Stephen Hawking made a prediction that seemed, at first, almost impossible to believe. Black holes, the very definition of inescapable gravity, might not be truly black. They might in fact glow, faintly, invisibly to our eyes, but undeniably, and over time, this glow would cause them to lose mass, to shrink, and eventually to vanish entirely. This idea, called Hawking radiation, changed the way physicists think about black holes, and bound them even more tightly to the laws of thermodynamics. To understand why, you need to leave behind the smooth, continuous fabric of space-time imagined in classical physics and step into the restless world of quantum mechanics. In this view, even the emptiest vacuum is alive with activity. Pairs of particles and antiparticles, matter and antimatter twins, constantly flicker into existence from the quantum foam, borrowing energy from nothingness, only to annihilate and disappear almost instantly. Normally, this dance leaves no trace, but near the event horizon of a black hole the rules bend. Imagine one of these particle pairs forming right at the horizon. One particle falls inward, crossing the point of no return. The other escapes, carrying away a tiny bit of the black hole's energy in the form of radiation. To a distant observer, it is as if the black hole itself has emitted a particle. Over countless such events, the black hole loses mass, its horizon shrinks, it grows slightly warmer, which in turn makes it radiate faster. The process accelerates in its final moments, ending in a brief but intense burst of radiation before nothing is left. For most black holes in the universe today, this is an unimaginably slow process. A black hole with the mass of our Sun would take roughly 167 billion years to evaporate, a number so large it is meaningless to compare to human lifespans, or even the current age of the universe, which is about 110 to the 10th power 10,010 years. A supermassive black hole, like the one at the centre of the Milky Way, would take even longer, 100 billion, 100 billion, 100 billion, 100 billion years or more. For these giants, Hawking radiation is a whisper so faint that it is utterly drowned out by the glow of the cosmic microwave background. As long as the universe is warmer than they are, they will gain more energy from absorbing background radiation than they lose by emitting it. And yet, given enough time, the balance will shift. As the universe continues to expand and cool, there will come a moment when the cosmic background temperature drops below that of even the coldest supermassive black hole. From then on, every black hole will begin to lose mass. The process will be glacial at first, but the end is inevitable. It is a strange vision, the far future of the cosmos, when all the stars have burned out and galaxies have gone dark. The universe will be filled only with fading embers, white dwarfs, neutron stars, and black holes, drifting apart in the endless expansion. Slowly, even those remnants will fade. The last black holes will outlive everything else, sitting alone in the void, evaporating at a pace too slow for any living thing to notice. And then, in one final moment, each will release a last flash of energy before disappearing entirely, leaving behind nothing but faint ripples of radiation in the dark. Physicists still debate whether something will remain after this final act. Some speculate that black holes might leave behind tiny, stable Planck-scale remnants, holding the last fragment of whatever information once fell inside. Others suggest that the information is not lost at all, but encoded somehow in the radiation, in a way we do not yet understand. This is part of the black hole information paradox, a puzzle that has driven decades of research and is still unresolved. Hawking radiation is not only a prediction about the distant future, it is also a bridge between the great theories of physics. It combines quantum mechanics, general relativity, and thermodynamics in a single phenomenon. Any complete theory of the universe will have to explain it naturally, without contradiction. This makes Hawking radiation not just an exotic footnote in astrophysics, but a key clue in the search for deeper laws of nature. From a more human perspective, there is something quietly moving about the idea that even black holes, so often imagined as eternal, have lifespans. They are born in the deaths of stars, they grow by feeding on matter and merging with each other, and they too eventually fade. The universe does not grant permanence, not even to the things that seem most unchangeable. Everything changes, everything flows toward an end. And yet, in the vast gulf of time between a black hole's birth and its final evaporation, entire histories can unfold. Stars can form and burn, planets can circle them, life can arise, civilizations can be born and vanish, all while the black hole remains, unhurried and unchanged for now. Its eventual goodbye does not diminish its presence in the ages when it still shapes galaxies, bends light, and stirs our curiosity. In the next part of our journey, we will step beyond the physics and into the human connection, what these strange, slow, powerful beings in the universe can teach us about our own place in it, and why thinking about the end of a black hole might help us understand the fleeting but meaningful light of a human life. In everyday life, information feels solid. A photograph can be lost, but somewhere the light it captured once reflected off a real moment. A letter might be burned, but the words once existed, carried by ink on paper. In physics, this sense of permanence is not just emotional, it is fundamental. The laws of quantum mechanics say that information, in the deepest sense, cannot be destroyed. The state of a system, the arrangement of every particle, every quantum property, must always be preserved, even if the details are scrambled beyond recognition. Black holes challenge that idea. When matter falls into one, it disappears from the universe as we can observe it. The atoms, the structures they formed, the patterns of energy they carried, all vanish beyond the event horizon. If the black hole then evaporates through Hawking radiation, the particles it emits are purely thermal. They carry no mark, no trace of what went in. It would be like shredding a book, burning the scraps, scattering the ashes, and finding that even the smoke has forgotten the words. This is the heart of the black hole information paradox. If the information is truly gone, then quantum mechanics must be wrong, or at least incomplete. If quantum mechanics is right, then somehow the information must be hidden, locked in the Hawking radiation in ways we don't yet understand, or stored on the event horizon itself, waiting to be released in the final act of evaporation? One possible answer comes from an idea called the holographic principle. It grew from studies of black holes in the 1990s, and it suggests something quietly radical. The information about everything that falls into a black hole is not stored inside it, but on its surface, the event horizon, in a kind of two-dimensional encoding. In this view, the three-dimensional interior is a projection of that surface information, much like a hologram produces the illusion of depth from a flat sheet. If the holographic principle is true, it might not just apply to black holes. It could be a property of the universe itself. Everything we experience as solid and three-dimensional could be, at the most fundamental level, the projection of information encoded on a distant boundary, the cosmic horizon that marks the edge of the observable universe. Black holes, in this sense, become laboratories for testing the deepest questions in physics. They are the one place where general relativity, our theory of gravity and spacetime, and quantum mechanics, our theory of the very small, must meet head-on. In the gentle curve of a planet's orbit or the precise ticking of an atomic clock, each theory works perfectly in its own domain. But inside a black hole, the extreme curvature of space-time and the restless fluctuations of quantum fields exist together, tangled and inseparable. It is here, at the edge of the event horizon, that we might find the key to a theory of everything, a single framework that unites the laws governing galaxies and atoms, stars and quarks, gravity and light. And yet, for all our progress, the event horizon remains both a window and a wall. We can calculate, we can imagine, we can even model the behavior of quantum fields in curved space-time, but we cannot look inside. The information paradox tells us that something essential is missing from our picture, something that might rewrite our understanding of space, time, and reality itself. Perhaps the most humbling part of the story is that this debate is not purely about faraway monsters in the dark. It is about the structure of the universe we inhabit, the rules that govern our own atoms, the limits of knowledge itself. If information can be destroyed in one place, perhaps it can be destroyed anywhere, even here, even now. If it can never be destroyed, then there must be an unbroken thread linking every state of the universe, past to present to future, with nothing truly lost. We often think of memory as fragile. We know how easily moments slip away, how photographs fade, how even our own recollections can blur with time. But the laws of physics whisper something different. On the deepest level, the universe might have a perfect memory, a memory that holds not only the grand motions of galaxies, but also the exact path of every particle of dust, every photon of starlight, every fleeting vibration of air that once carried a human voice. Black holes seem to test that promise. They ask the most difficult question a universe can pose to itself. Can I forget? The answer, if we ever find it, will not only tell us about black holes, it will tell us whether reality itself is a story that keeps all its pages or one that sometimes burns them. From here, we will take one final step outward, away from the equations, away from the paradoxes, and look at the long arc of our own existence in this vast, intricate universe. We will remember that we too are made of the same matter that black holes challenge and protect, and we will see that our lives, brief as they are bound into the same story the cosmos has been telling for billions of years. If you trace the history of every atom in your body far enough back, you find a journey that is older than the Earth itself. The oxygen in your lungs, the calcium in your bones, the iron in your blood. All of it was forged in stars that lived and died long before our sun was born. The hydrogen in your body is older still, made in the first few minutes after the Big Bang, when the universe was still glowing with the light of its own birth. You are quite literally made of stardust, and in that sense you are kin to every planet, every comet, every drifting cloud of gas, and even to the black holes that sit in the deep heart of galaxies. It is tempting to think of black holes only as destroyers, They swallow light, crush matter, and lock away anything that crosses their event horizon. But their existence is tied to the cycles that make the universe rich in complexity. Without the deaths of massive stars, the supernova that leave behind black holes, many of the heavier elements we rely on could never have formed. The gold in a wedding ring, the iodine in a human thyroid, the uranium deep in the Earth's crust, all of it came from the titanic forces unleashed when stars died, sometimes in the very moments before a black hole was born. In the larger scales, black holes act as architects as well as inheritors. Supermassive black holes, millions or billions of times the mass of the Sun, sit at the centre of nearly every large galaxy, including our own Milky Way. Their gravity shapes the flow of stars and gas. When they feed on matter, their accretion disks blaze with energy, releasing jets that can travel for thousands of light years. These outbursts can quench star formation in some regions while triggering it in others. They can sculpt galaxies into the forms we see today, regulating the growth of entire stellar cities. And yet, for all their power, black holes are not separate from the rest of the cosmos. They are not outsiders. They are made from the same raw material as everything else. Their atoms, before they were crushed beyond recognition, were born in the same furnaces as ours. In the most literal sense, we share an origin. The universe recycles itself endlessly, folding matter and energy into new forms, each shaped by the same physical laws. It is here that science begins to touch something that feels like philosophy. When we look at a black hole, we're not just looking at an object. We are looking at one of the ways the universe learns to arrange itself. We are seeing the consequences of gravity and time, heat and light, matter and motion, the same forces that shaped us. Our lives are small in scale compared to the lifespan of a black hole, but they are built from the same story. We are also, in a sense, the universe observing itself. The atoms in our eyes, our hands, our thoughts, once scattered across space, have found their way into patterns capable of asking questions, of wondering about the very stars and black holes that gave them form. When we study the cosmos, we are part of the cosmos studying its own history. When we marvel at a photograph of a black hole's shadow, it is the stardust in our brains recognizing a relative across unimaginable distances. There is something deeply peaceful in that perspective. It does not erase the strangeness or the danger of black holes, but it softens them. They are no longer alien predators in the dark. They are part of the same family of matter and energy to which we belong. They are extreme, yes, but not separate. And perhaps that is why they hold such fascination. They are like mirrors that show us not our reflection, but the extremes of our shared reality. In their gravity, we see the bending of the same space-time that cradles us. In their event horizons, we see the limits of the same physics that governs our cells. In their evaporation, we see the slow passage of time that will one day touch all things, even the stars. As our journey comes to an end, imagine yourself drifting in the quiet of space, far from any star, with only the faint glow of distant galaxies around you. Somewhere, a black hole spins slowly, its event horizon silent, its gravity reaching out in all directions. You're not falling toward it, and it is not hunting you. It is simply there, as much a part of the cosmic landscape as the light of the Milky Way. In this moment, there is no urgency. The universe is vast, and your place in it is real, even if it is small. You are made of the same matter that stars burn, the same particles that black holes swallow, the same quantum threads that hold the cosmos together. You carry within you the story of hydrogen clouds and supernovae, of galaxies forming and colliding, of time flowing and bending. You are not apart from the universe. You are a chapter in its ongoing book. So as the black hole sits in its quiet orbit, and the stars drift slowly in their courses, you can rest. The universe will go on, and for now, It holds you in the same fabric that holds everything else. Sleep, knowing that you are made of the cosmos, and that in some quiet way, the cosmos is made of you.